Okay, so let's talk about the graph traversal algorithm, DFS. As you know, DFS is depth first search. And like BFS, here also we need, since this is a graph, we want to make sure that if we visit a node already, right, we don't want to visit it again. So we have a visited list here. And then we are going to have a stack data structure, right? So we'll have a stack. And we know the principle that stack follows is last in, first out, right? Okay, so let's start from A. And again, this graph is represented, say, using a adjacency list, or it can be adjacency matrix. Anything is fine. So it's the same thing, DE. So the list for A's neighbors are, say, B, C, D. For B, it's A, E, and D. For C, it's A and D. For D, it's A, C, and E. And for E, it's B and D. Okay. So initially what you do is we put, say, we can start anywhere. So let's start from B this time. So we put B here in the stack and also put B in the visited list. Then we start here and then we take out B from the stack. So that means we take out B and we put the B's neighbors, say A, E, and D into the stack. Okay, so we put A, E, and D, and also put them into the visited node. Next, we take out D, right? Because this is the last one that went into the stack. So we take out D. And then these neighbors are like A, C, and E. Now you see A is already in the visited list. C is not in the visited list. E is in the visited list. So what we do is we just put C. Okay. So next we take out C. Oh, okay. We put C and then add C to the visited list. Next we take out C. Okay. So once you take out C, then we check C's neighbors, A and D, both of them are in the visited list, so we don't add them. Next, we take E. E's neighbors are B and D, both of them are in visited, so we don't put them in this stack. The stack now only has A. I take A out, and you see is all three neighbors are already in the stack, right? Okay, so you see here that this depth first search initially went all the way to this, like as deep as possible, right? And then it started coming back and check this is visited, so it started further going back to visit this, right? So it's B, D, C, and then it comes back to D, and D is already visited, so it goes to, it visits E, and then from E, it again comes back to D, it's done, it goes back to B, it's done, and then it goes back to A. Okay, so this depth first search, since you are using a stack, it goes as deep as possible, and then it comes back. So the trick here is to use a stack and also a visited list. So if you remember, we can also do the DFS recursively. I would suggest to look like this is the other homework to see how we can do this DFS on a graph recursively. Okay, so let's try to find out the time and space complexity of DFS algorithm. So this is a pseudocode for DFS. We are given an input graph, right? So in the input graph can be in the adjacency list format. That means we'll have the list of vertices, say any vertex. So these are the list of vertices. And this is the list of edges for each vertex, right? So X has suppose two neighbors, A and B, something like that. Similarly, other vertices will have their neighbors. So this is an adjacency list representation of the graph. So given this, we initiate a stack and a set or map visited. We start with pushing any node X into S and make it visited. Okay, so doing all these, we are doing like order of one work here, right? Okay. And then until the stack is not empty, what we do is we pop one node. So in total, how many pops will happen? Order of V in total, right? Order of V pops will happen if all the vertices are inserted into the stack throughout the algorithm. And for the popped node, we'll check, say we pop this node. So we'll check all the neighbors and we'll see that if any of those neighbors are, and we'll check if which of those neighbors are still not visited. So say the neighbors are denoted by Y. So if it's an unvisited neighbor, we visit it and push that neighbor into the stack. Okay, so in total throughout the algorithm, how many times we will check the neighbors, right? It will check it order of E times. You get that? Okay, so in the total amount of work is going to be order of V plus order of E. So that is the time complexity of DFS algorithm. Now, what about the space complexity? Now, the space complexity is how much extra space we are using, right? So here you see that we have a map visited, right? So this one will contain V vertices eventually. And the stack also may at some point contain V vertices. That means the space complexity is order of V. Okay. We can rewrite this one as order of V plus E. So there goes the time complexity and the space complexity of DFS algorithm.